Okay, our next speaker is Aleksandra Radjenovic from the Glasgow Math and Healthcare Center.
Yeah.
And Sasha will speak about quantitative interpretation of multi-parametric cardiovascular MRI.
Thank you, Carla. I am bringing you greetings from your sister center, the Center for Multiscale Soft Tissue Mechanics, that's coordinated from Glasgow, and it has many varied and interesting work packages, and I reside in a little corner of work package 5, looking at supplying quantitative MRI data sets for a multiscale heart modeling in myocardial infarction. Now, in a little homage to one of the colleagues sitting here, Martin, I will give you a short case study presentation that reflects the title of his beautiful introductory MRI book, Picture to Proton. So I'm going to show you some results, and then I'll slowly walk you back to the methods and the origin of these results. Now, I'm interested in microcirculation, and I would love to be able to see an image like that using MRI, which, despite being so powerful and versatile, is not likely to give us images like this anytime soon, even with all the compressed sensing or anything else. I was very impressed to see the image you showed, Carla, of little red blood cells flowing through the tiny capillaries. That's stuff of science fiction for us in the MRI. I know, but we would like to see this, but we know we can't, and we want to, I would like to try and explain to you why MRI is worth persisting with, despite the fact that we will never be able to see images like this. So, if we look at the things that MRI is good at, it is good at depicting alterations of tissue structure and function. And why is this so important for medical diagnosis as well as for biomedical research? Is that in most human diseases, the pathological cascade looks something like this. You have a set of molecular events, you have a set of cellular events, then you see changes at the tissue level, and then you get clinical symptoms. And where MRI comes into its own, where it's without competition in the clinical imaging arena, it's in this sense that it is able to give us quantitative parameters describing tissue changes way before the onset of clinical symptoms. So let's start this little retrospective story. In a very recent study completed at our center, we have found out through MRI that fractional blood volume in left ventricular myocardium in a set of 33 subjects is 0.11 plus minus 0.03. That's a unit 3 number depicting the fraction of tissue occupied by blood. We have also determined permeability surface area product using MRI only, and the value is displayed here. Now, if we break down this average value into subjects that we studied in this little project, you will see that we see a pattern that is very interesting and also very important in terms of understanding the nature of very early cardiovascular changes that affect patients with chronic kidney disease. We also see very interesting patterns, differences between gender values in FBV, in fractional blood volume is significantly lower in males in both disease and health. And we also, for the first time, described here, again in this very simple study, that there is a level of inflammation or probably inflammation-regulated vasodilatation in patients who suffer with chronic kidney disease. So I will now show you very briefly where these numbers come from. So if we look at this slide here, pick one of the numbers, this is where the numbers come from. We have measured pairs of values of T1 relaxation or its inverse R1 in blood pool and in myocardium in response to pulsed injections of ferromoxetol, which is iron-based contrast agent. That contrast agent is contained within blood vessels, and from the difference in response, in MRI response measured by R1, at each time point here, we build up a picture of the pattern of change of R1 in myocardium compared to R1 in blood. And then we subject these measured values to modeling, and we obtain a single value that goes into that, single pair of fitted values that goes into that graph I showed earlier. Now, where these numbers come from? These numbers come from a 3-compartment, 2-exchange sites model that is described by this set of differential equations, where we basically model the magnetization changes in the tissue sample, not as a uniform block of tissue, but we separate them into components related to blood, interstitium, and cells. We then incorporate these exchange processes into block equations, and then compute our overall bulk vector m as a function of time. Then from that vector we infer what bulk relaxation rate R1 would give us that particular m, and then we try to minimize the departures between our measured values and fitted values, and we find the optimal values of parameters KIB and also a fractional volume of blood in the myocardium. Now, if I show you where, even further back in time, where the numbers come from, for each one of the points on this graph, okay, we have to acquire at least 8 inversion recovery images in order to compute T1 times. So you rapidly get a sense of how complex this measurement is. So we basically acquire typically 5 or more T1 maps in response to pulse injections of ferromoxetol, and then we compute these maps, fit them into this model, and then look at the changes between different subjects. Now, if I tell you very briefly what our problem is, this is the part where I do the challenge pitch. Imagine all the effort that went into collecting these 33 data sets, CKD patients, very ill, 1 full-time clinical fellow working on the study, full-time. Hundreds of man-hours go into producing every individual data set that I showed you in the first picture. And now what happens when we finally get the spatial maps, that reflect particular physiological parameter? We are then faced currently with the need to smash it, to destroy it, to fit an accepted grid that's proposed by American Heart Association, and then report it, regardless of the resolution that we acquire it in and trouble we go through. We need to use AHA model to report it in our papers. And I have to stress here, as a clinical physicist, somebody who works on the front line of data collection, reducing spatial resolution in MRI is criminal. It takes us so much effort to increase spatial resolution. We fight against limitations caused by signal to noise. Once we acquire it, we don't want anybody to do any smoothing or any reformatting, okay? So what happens? Basically, we get these beautiful complex images, then we have to divide them in these six sectors. Instead of trying to using either atlases or elastic deformation to map them to their natural state, but preserve their resolution. By preserving their resolution, interpolating them in an intelligent and robust way so that we retain our acquired resolution and never go below it. So this would be particularly important in looking at longitudinal changes or complex measurements that I described earlier, where you not only need to co-register or regularize images acquired inside a single imaging session, but you look at images acquired in separate breath holds several minutes apart, and then look at longitudinal changes that can occur over a period of years. So with that, I want to remind you of what we can't see, but I'd like to reiterate that even though we can't see the capillaries, we can infer an awful lot of information about their environment and their function. And I want to thank all my colleagues who collaborated on this. These are the people who actually put these hundreds of man-hours into producing this small set of results. So thank you very much.